So welcome. I'm very excited about this event and all the new connections we can make. I think IPAM is all about building connections, and this is a great venue to discuss a really important topic. So so I'll be talking about how math is changing. I think we've seen it sort of the hype build up over the last few years of how AI and other tools are becoming more and more capable in math and other tasks. But this is the year where I think it's really beginning to happen. And to be honest, math is kind of overdue for some reform because in many ways we are an extremely conservative field, not in the political sense, but in the sense of practice. I'll just give you two examples here. So here is a memoir from exactly 200 years ago, 201 now, from Cauchy, introducing most of foundational complex analysis, so the Cauchy integral formula, for example. And the book is written in French and not in LaTeX, but other than that, it is almost identical to a textbook that you would see today. I mean, the way we teach mathematics has changed only in sort of secondary ways. But a graduate student studying complex analysis would basically recognize everything in that book. Also, we're still very attached to our blackboards. You can see we're almost the only discipline left that still uses our blackboards, and it's to the point where photographers and think that this is it's an art form. Actually, there's a little coffee table book by Jessica Wynn, actually, who I know actually, who actually which is a very nice book, just visiting a mathematician and just photographing their blackboards as just an unusual art form that you don't see anywhere else. So, so we are kind of unusual. For example, we don't collaborate very much, at least not until very recently. So even among the other physical sciences. This is a plot which is already 10 years old, but just plotting the number of co-authors in a paper between, say, math, chemistry, and physics. And math has been stuck at like 1 or 2 collaborators for decades. And the other sciences are beginning to realize that actually, the modern research tasks really require broad collaborations and very diverse sets of people, and we haven't really done that yet. So we're kind of missing out on kind of the scaling up or industrialization of science. Now, there's reasons for that. It's not just because we are antisocial, even you could. But there is, so there is a high barrier to entry. Like with a mathematics problem, you often need a math PhD to even understand what the question is. And our standard of proof is extremely high. We are interested in, when we want to prove something, we want every step to be absolutely correct. So if you're collaborating with 10 people and one of them is unreliable and is producing untrusted arguments, either everybody has to verify everyone else's arguments, which is very tedious, or your proofs are rubbish. And a lot of our workflows don't scale. So blackboards are lovely when you have 2 or 3 people. I mean, it's an amazing experience, actually, to just solve a problem at a blackboard with someone who you're really mentally tuned to. But when you have 20, 50 people working on the problem, and they're all in different countries and so forth, you can't really solve a problem over Zoom, for instance. It doesn't really work. There are reasons why we sort of haven't changed with the times as much as other disciplines. But I think now, with all the technology, this is going to change. So we are finally, in the last year or two, beginning to create large-scale projects. So the analogy I like to give is that in the experimental sciences, there's a distinction between case studies where you take one particular object of study and you make a very intensive, detailed analysis of that one object. And that's kind of the standard thing you do in mathematics. You take one mathematical problem or one mathematical concept and you study it very carefully. But then there's population surveys where you take a population of 1,000 members of a species or whatever, and you do data analysis. You do statistics. What percentage of your population does this? What percentage of the population does that? And we don't do that in math because we haven't had tools that can sort of systematically study large populations of problems until now. we are finally beginning to do broad participation. So in the other sciences, sometimes there is citizen science. You can have amateurs collect butterflies or identify comets or take water samples, and even if the data, if the quality of the data is not sort of up to 100% scientific standards, there are ways to still use that somewhat noisy data. And until recently, we couldn't do that with math. I mean, outside of a few isolated projects like finding large primes, there's a few things where you could get amateurs. But now we can do that too. So that we are beginning to have projects where many of the contributors are not professional mathematicians, but graduate students, high school students, people from computer science or from the tech industry with some spare time. So we are finding projects where lots and lots of people can contribute in interesting ways. And of course, AI. So AI is advancing really rapidly and can really help these projects in real time now, and in ways that sort of save more time than they waste. And that we've sort of passed this crossover point. And then there's a secret ingredient that makes all this work. The reason why scaling and AI and broad participation actually is a net win is because we also have formal verification. There's a lot of advances in actually automatically checking whether a certain argument is correct or not. And so even if a lot of the contributions coming from AI or from the general public or from a very large-scale project are unreliable, we have ways to filter out the untrustworthy inputs and keep the good ones. And that has made a huge difference. So I've given versions of this talk for several years now. And I've usually sort of pinpointed individual examples of places where AI or neural networks or whatever have made some progress. But as I said, we're now entering the era of scale. So I will talk actually just about one population study, if you wish. I call it a case study here, but it's one which is kind of made, it's been sort of buzzing in social media now, which is the Erdös problems, which are sort of the first large data set of problems for which we can actually apply all these tools and get some idea of which ones are working and what the strengths and weaknesses are. So the Erdös problems are a collection of about 1,000 odd problems, and there's a website started about 3 years ago by Thomas Bloom to systematically cover these. So Erdös was a mathematician active in the 20th century, very, very prolific. He authored over 1,500 papers in mathematics. I think that's still the record. And he collaborated with everybody. I mean, he didn't collaborate with me, okay? But I did meet him when I was 10. That's a picture of myself with Paul Erdös. So he loved giving out problems. When I met him, he just basically gave me a problem, and we worked on it. We didn't solve it. It did get solved later, actually. But he was very, very fond of giving out problems to encourage the community to get interested in the type of mathematics he was promoting. And so he was famous for not just his research, but for posing problems constantly. Yes, he even put cash prizes to some of these problems. So some were actually with, most are like $50, $20, and nothing significant. But there were a few that are really quite influential. Okay, so this is one of the Erdös problems. It doesn't matter what it is, but it's for the purpose of this talk. But it's been one of the most influential questions. How big does a set need to be before you can show that it has arithmetic progressions? This problem, he attached one of the biggest prizes, $5,000 to it. And it's still open, but there are many. I've worked on aspects of this problem. There are many partial results towards this problem that themselves appeared in top journals. It is a really influential question. He had a knack of asking really good questions that are not impossible, are not trivial, but just at the border where he knew that any progress would be interesting. So Erdös called these problems acorns, requiring deep and subtle new insights from which a mighty oak can develop. Okay. However, he posed 1,000 odd problems. They were not all acorns. So there were some problems which turned out to be ridiculously easy, in fact. So here's another one he posed. There's a certain equation, n factorial equals x to the k plus or minus y to the k. Are there any solutions to this equation? So like a Fermat's last theorem type problem. So he asked this, and it turned out he posted in, it turned out after a couple of decades that you just take a computer to search, and the answer is no. There's a simple example. You can actually just numerically show this answer is false. But Erdös knew this. Okay, so he called these problems marshmallows, serving as a tasty tidbit, allowing a few moments of fleeting enjoyment. So it's a very diverse set of problems. These problems. And I should insert some disclaimers because in social media, recently these AI companies say, we just solved 5 Erdös problems. No, we solved 6. Okay, the implication is that this is what mathematicians do all the time. Is that we are just trying to solve these problems. I should just preface this is that. The Erdös problems, problem solving is only one aspect of mathematical research. We are also interested in understanding concepts and communicating and simplifying things. And the reason we solve the problems is not so much because the problem itself has all these applications, but it's because the process of finding the solution often discovers new. So many of the Erdös problems, there are new techniques. This problem of finding arithmetic progressions, it led to the whole field of additive combinatorics, for instance. It's not just getting the solution, but sort of all the things that come with that usually when you work towards a solution. But nevertheless, there's 1,000 problems, and some are solved, some are unsolved. To a computer scientist, it looks really much like a benchmark. It is not a benchmark, but it's become a very tempting target because it's you can actually measure. Here's your new AI tool. How many Erdös problems can it solve? I think it is a nice data set for the state to sort of take a snapshot of where these tools are at this moment in time. And you can start doing comparative tests of what types of ways of using AI are more effective than others, which it's harder to see if you're just studying, if all you're given is 1 or 2 problems that have been solved by AI. But we have 1,000. You can start doing things like data analysis. So there has been a lot of hype. So I should say right away, okay, so even though there are major important problems in the Erdös problem set, currently the AI has not really made progress on the most high-profile problems, the ones that mathematicians most want to solve. To date, the problems that it has solved are the ones that are attention bottlenecked, the ones for which Erdös posed once or twice in a paper, but there's been almost no follow-up literature. No one has really looked at them, but AI can scale. And so we are sort of clearing out, making progress on a lot of problems for which we didn't really have enough human attention on. But even with all the hype, there has been a really visible increase in capability. I mean, it is not pure hype by any means. And to me, what these advances show is that there is a complementary way to do mathematics. So humans, traditionally, we work in small groups on hard problems for months, and we will keep doing that. But we can also now set AIs to scale, to sweep 1,000 problems and pick up all the low-hanging fruit, if you wish. I figure all the ways to come to match. They have 20 different techniques. Apply them all to 1,000 problems and see which ones can be solved by these methods. This is the capability that is present today. And as I said, we can do statistics. Okay, so I can ask, how are we doing the Erdös problems? I can give you graphs. We started tracking this systematically just last September. What are all these graphs? Okay, so this is the number of unsolved problems. Okay, so right now there are, of the 1,000-odd problems, there's 699 are unsolved. The reason there's a big spike here is that at one point Thomas discovered a big trove of new Erdös problems, like 50 or so that he added. Okay, so. And how many are solved? 480. And it's been just increasing steadily for many reasons over time. AI started making big progress around here. Well, actually, there was a spike here also when literature search came out. Okay, so AI research tools had discovered a whole bunch of solutions that were in the literature, but we hadn't recorded them. So there's an early spike, and then there's been this acceleration. Although currently there's been a plateau. The last few weeks there hasn't been much activity. I think because there's another benchmark came out and it's been attracting a lot of attention, but that's my theory. And some other, and also we've been making progress formalizing a lot of the solutions. So not only are the solutions, many problems solved, but we've actually started formalizing them in this language called Lean. So a lot of solutions are now also formalized. Okay, I won't talk about the other curves. So we're beginning to make progress. Some of the progress is kind of mundane. Well, it was amazing 6 months ago, and now we think it was mundane. It's like saying web search. You know, I remember when Out of Easter and then Google came out in the early 2000s, and my jaw dropped just how amazing it was that I could access the entire internet. You know, and we just take it for granted nowadays. And it's beginning to be like that too. So 6 months ago, these deep research tools came out, and you can get an AI to search all kinds of literature and find obscure matches to your problem and say, oh yeah, there's a paper from 1970 which has in a different language, often literally, but in a different field, but it solves the problem with a tiny bit of modification. So we basically have semantic search now, which we've been wanting for years. They still occasionally hallucinate bad references, but at least with literature search, you can go and check the source material. So, 20, 30 odd Erdös problems were solved this way. Everyone, I mean, it's extremely easy now to use AI to generate code and numerical data. You can do much more numerical generation. And we can formalize so much faster now that the translation of an informal proof to a formal proof to check was really tedious. It took weeks. Now people can do it in hours. Well, not for every single paper, but for many types. And this has been important for being able to work with AI, because if someone says, hey, I've solved this problem, and here's an AI-generated proof with like 5-6 pages of AI-generated text, it's often got rubbish in it, and no one has the time to look through all these things. But we can now automatically convert them into formal proofs. Sometimes it works, sometimes it doesn't. And so we can actually handle a big influx of AI-generated solutions. This is a typical deep research. So here was an Erdös problem, which turned out that you just asked, was this problem being solved? And yes, it was solved by, in this case, by Erdös himself in 1981. So at least 20 problems have been solved this way. Here's a recent paper I wrote on another Erdös problem. This one I didn't use much. I used AI to convince myself the result was true, and I used AI to draw pictures. Okay, I mean they can draw professional grade plots, and it just it's much better than much faster than messing around myself with Python or whatever. I mean just for secondary things like this, AI is already basically excellent. And this is what a formal proof looks like. Here was a proof that was first published like 10 years ago, one of the Erdös problems. And there's a talk at Aristotle that converted it into Lean. Lean looks kind of a mix between math and Python. So this is what a proof looks like. You'll see there's always squiggly lines. The formal proof sometimes has some oddities. Like Aristotle likes to use deprecated methods, for example, that still work for now, but they're being phased out. The proofs, when you, to someone who's expert in this language, they look a little bit verbose and not quite polished. But this is something which I think will be improved upon. But maybe it's not so important because in many cases you don't really care exactly how elegant the proof is, as long as it compiles, you're happy. We're using all these tools. Another thing that has been the reason why we're making so much progress also is that we have a community now. So Thomas has actually worked really hard to build a community. There's this discussion forum and community roles. Importantly, we're neither sort of overly pro-AI or anti-AI. I mean, some others, different forums have all kinds of attitudes towards AI. So I think what has made the Erdös problems particularly amenable is that we welcome people to contribute AI-generated solutions, but there are rules. You have to disclose them. You can't just have a long string of text and pretend that it was a human that came up with it when obviously it wasn't. And you have to summarize. You have to be responsible for the content. And you can't just spam the doc. If you have a really long thing you want to say, you put it in a link. So there's some reasonable rules, and it's actually managed to work. So in In other forums, there's a real concerns about being flooded by AI-generated slop, I guess is the modern term. And we've had to moderate and delete some comments. But actually, by and large, we've had constructive discussions between both people who are doing math traditionally and through AI. Okay, so just very quickly, I'll just give some actual examples of how humans and AI have interacted on the site. Here is an Erdös problem 367. It is still unsolved, technically, because it asks two questions about a certain number theoretic object. It doesn't matter what the quantity is. It asks for two inequalities. And AI was able to prove one of them. The other one is still open. Well, not AI precisely, humans and AI. So what happened was that a human on the forum, Walter, played with it, and he said, okay, I got a construction which he did some numerics, I think it works, but there was this one identity that he had to prove. He plugged in a certain construction, and as long as a certain congruence condition held, he could solve the problem. And he said, I'm sure someone is able to verify that this holds. Okay. He could check it with the first few cases numerically. I logged on the site. So instead of working out pen and paper, I just gave it to Gemini. And Gemini just proved the missing step. This was about three months ago or so. Using rather way fancier technology than was needed. I used the 5-adic valuations and some algebraic number theory. But I could read the proof. I translated it into something which was sort of simplified. So then I explained it on the forum, and then a third person, Boris Alexeyev, took that proof and just fed it into one of these AI autoformalizers, Aristotle in this case, and converted it into a lean proof. So checked out, so we have a completely confirmed proof of that result. So that's sort of a typical interaction. Another example, and that's the final example I think for this talk. So there's another problem which actually we did fully solve, 1026. So it's an optimization problem. Okay, so there's a mathematical description, but actually I asked Nano Banana to give a condensed explanation of it. So you can think about it as a coin game. So two players, Alice and Bob. So Alice has a stack of coins, and she will split them into n piles. So n is given like, say, 10. Okay, so you want to split your pile of coins into 10 piles. Some are tall, some are short. So you have 10 piles, and then Bob will select some of the piles to keep for himself. But the rule is that Bob can only select an increasing sequence of piles or a decreasing sequence. It cannot select an alternating sequence. So Bob might select, for example, this guy, and this pile. But it can't select this pile, this pile, and this pile, because that's neither increasing nor decreasing. And Bob will select the combination of powers that gives him the most coins. And Alice will try to arrange the coins so that she loses the least amount of coins. And the question is how much, what should Alice charge Bob to pay this game? What is the fair price of this game? So as a fraction of the total number of coins. So that's a quantity called C of n. And basically the question is, what is C of n? That is the question that Erdös asked. So the way this worked is that one of the participants on the forum just started working this out with small n using some linear programming, and worked out what the ratio was for small n, and made a conjecture that if you had a square number of piles, k squared, then the optimal cost is 1 over k. So if you have 16 piles, Bob can basically take 1/4 of Alice's money. It turned out actually that this was not a new conjecture, that actually, later on we actually ran a deep research tool. This exact conjecture was made back in 1980, but we didn't know about it. And then nothing happened for 2 months. No one was able to solve this conjecture, except at some point, Boris decided to just put this conjecture into Aristotle and see if he could just solve it. It's just a finer proof, and formalize it in lean. And it did. So I think he tried it for like hundreds of problems, and the success rate was like 1 or 2%. But this one he did, and the proof was quite interesting. Like this coin problem, he managed to convert into from packing little squares into a big square. There's a simple translation which I won't mention here, but it caught us by surprise that the AI could do this. We did later find that there was precedent for this trick of encoding this type of monotone sequence problem into a packing problem by a paper from 1959. And also we also later found that this particular problem that it solved was already solved by a different method in 2016. So this by itself was not a novel, a proof of an open problem, but it was an interesting method and rather creative. But it only solved the square case. It only solved, with the number of powers was a squared, 1, 4, 9, 16, it worked, but what about the other ones? Okay, so with numerics, you could get up to like n equals 8 or 9, but with linear programming. But at some point, the linear programming became exponentially big and you couldn't do it. So I used a different AI tool called AlphaEvolve to work out extremizers for up to 16, actually. So, I just ran this tool and it gave me, here are sort of the optimal, or at least an optimal, or probably optimal configurations of coins. And there were various patterns that you could see, and it gave values of the C of n. And based on that, I could make a conjecture as to what it was. I first made a rather complicated conjecture, and then Bars simplified it to a much simpler conjecture. And then a further co-author, Lawrence Wu, who I think works at was it OpenAI? Yeah, so he noticed that this conjecture was very similar to, well, either he or Hugh plus an AI, I'm not quite sure exactly, but yeah, it was actually, it was almost exactly the same function appeared in a different problem, which actually was a separate Erdös problem about square packing. And that problem had just been solved. So there was a question about square packing that was just solved like 2 years ago. Using actually with a function which was almost, in fact, turned out identical to the one that we had just conjectured, and so just by putting that together with everything we've done, we solved this problem 1024, and it's now also formalized in Lean. So it's a fascinating interplay between humans and AI. So just to wrap up, yeah, so AI, it's already enabling all kinds of new ways to do math at scales we haven't seen before, at speeds we haven't seen before, and really broad. You know, most of these people I've met online, a few of them, but not met most of them in person. But I think what's really important, like once you collect a systematic set of things to do, problems or tasks, lots of good things start happening. I mean, in computer science, I think we've known this, that once you get a good data set, you can do all kinds of things. But mathematicians, we haven't put enough value on data sets. But this is, I think, it's the foundation. Once you have a good set of things to do, there's just so many tools out there and so many people who may not be professional mathematicians who are just willing to experiment, that you can start getting all kinds of unexpected progress. And yeah, in particular, I think because of this, they really lower the barrier yeah. So you know, there are Erdös problems that were basically solved by high school students with armed with an AI, and that's great. But you know, and we've been able to check it because it's in Lean. Yeah. Yeah. So yeah, the other thing is it's really important that we have this verification. Okay. Everyone has seen what happens if you allow unverified AI to take over a site or something. Yeah, and I really think, you know, so AI by themselves are already great, but I think there's so much potential in human AI collaboration, yeah, particularly for sort of long tail applications. So far, working on the hardest problems, it's really not clear how to apply any of this to individual really hard problems. But if you have 1,000 medium difficulty problems, then AI is great. So I think I'll stop there. Thank you.